So while estimating the length of air gap, the points to be considered are: number 1, points to consider. Consider while estimating the length of air gap. Estimating length of air gap, LG. Point number 1 is power factor. Point number 2 is overload capacity. Overload capacity. Point number 3 is pulsation loss. Point number 4 is unbalanced magnetic pole. Unbalanced magnetic pole. Point number 5 is cooling, and point number 6 is noise. So these 6 points we have to consider while estimating the length of air gap between stator and rotor of 3-phase induction motor. Now considering all the points one by one. Point number 1, power factor. Power factor. So here 2 machines we will be considering. Machine number 1 having comparatively small air gap, and machine 2 having comparatively large air gap. Let Vs is the applied voltage. Vs applied voltage per phase. Phi m is the air gap flux. Air gap flux. ER rotor induced EMF. Rotor induced EMF. IR rotor current. IR dash. This is rotor current refer to stator side. IM magnetizing current. I this is loss component of current. Loss component of no load current, IO. IO no load current. IS stator current. stator. Now plotting phasor diagram for machine having small air gap and large air gap. Vs, this is applied voltage, Vs. First phi m is plotted. This is air gap flux, phi m. This is stator applied voltage per phase. As air gap is small, no load current taken by the motor is small because length of air gap is small. So this is Im, no load current. This is IO. No load current have two component, magnetizing component Im and the loss component II. Magnetizing flux produced ER in the rotor. And therefore current IR set up in the rotor as it is short circuited. IR set up in the rotor. This current, rotor current, is reflected back into the stator side. This is IR dash, IR dash, and phasor sum of rotor current IR dash and the no load current IO is the stator current IS. This is phasor diagram for the induction machine, and this is the power factor angle phi. So this is phasor diagram for the machine having small air gap. So we can say this is phasor diagram for machine 1. So this is magnetizing current for machine 1 having small air gap. Loss component of current II1. Rotor current IR1. Rotor current reflected into the stator side is IR1 dash. This phasor sum of no load current and IR1 dash is the stator current IS1, and the angle between Vs and IS1 is power factor angle phi 1. This is for machine 1. Now phasor diagram for machine 2 having comparatively large area. So this is phi m, air gap flux phi m. As air gap is large, more magnetizing current is required. So this is the magnetizing current, more magnetizing current is required. This is I0 no load current. This is IM2 for machine 2. This is loss component II2 for machine 2. Now phi m is linked by the rotor, therefore EMF induced in rotor is ER. Current set up in the rotor is IR2. This is reflected into the rotor side is IR2 dash, and no load current and the IR current gives stator current IS. For machine 2 it is IS2, and this is power factor angle phi 2. This is Vs applied voltage. The phasor diagram 1 is for machine having small air gap and phasor. So phasor diagram 1 is for machine having small length of air gap Lg, and phasor diagram 2 is for comparatively having large air gap. So it is clear from the phasor diagram that if length of air gap is large from phasor diagram, if length of air gap Lg is comparatively large, then magnetizing current is large. Magnetizing current Im is large. Therefore, power factor angle phi 2 is increased, and therefore power factor cos phi is decreased. So machine 1 having small air gap, small Lg, therefore power factor is good. So this is clear that the machine having small air gap, power factor is good. Now second point. The second point to be considered is overload capacity. Overload capacity. Overload capacity is a ratio maximum output upon rated output. This is overload capacity, and this can be the maximum output of the induction motor is obtained from the circle diagram shown below. Circle diagram. The overload capacity is Mn. This is Mn upon Al. So this is maximum output and this is the rated output. So we have to see the circle diagram. This is applied voltage. This is the x-axis showing current. This is no load current. This is plotted at an angle phi 0, no load power factor angle obtained from the no load test. So this is I0. From I0, this is horizontal line is plotted. This is the diameter of the circle. C is the center of the circle. Then OB is the short circuit current of the motor, ISC, when normal voltage is applied and current and the rotor is blocked. This is IS short. Taking O-C as a center of the circle, and circle is plotted like this. This is the circle diagram of induction motor. This B and this F is divided in B and this F is divided equally. So this is the center point BG and the GF. This is stator copper loss and the rotor copper loss assume equal. Therefore G is the center point, and this is plotted. O0 is joined with G. This is the torque line, and this is I0, no load current, is joined with B. This is the output line. 90 degree to output line, point OM is plotted, and from point M perpendicular is drawn on the output line. So this is the output, maximum output for machine having small air gap, and this is the tangent to the portion, tangent to the circle. This is showing OA is the rated current, and from rated current line is plotted on the output line. So this is the rated output. AL shows rated output. So this is for minimum air gap, and this circle diagram is for comparatively large air gap. So diameter of the circle is Vs upon XS1. XS1 is the stator reactance for the machine 1 having small air gap, and XS2 the machine having comparatively large air gap. So in this it is clear that if length of air gap is large, so diameter of the circle diagram is, as we know, diameter of circle diagram is Vs upon Xs. So Vs is the supply voltage, rated voltage, and Xs is the reactance depending on the length of air gap. So if Xs is small, greater is the diameter of circle diagram. Diameter of circle diagram increases for constant Vs. If Xs is small, diameter of diagram increases, and value of Xs depend on the length of air gap. So if length of air gap is Lg. If length of air gap is increased, then leakage reactance of the stator is decreased, and therefore overload capacity increases. Overload capacity increases. So from the circle diagram we have seen that the circle diagram 2 is for small air gap and circle diagram 1 is for comparatively large air gap. So point number 3 is pulsation loss. Flux pulsation loss. So if length of air gap Lg is increased and flux pulsation loss decreases. Flux pulsation loss decreases. Therefore, efficiency increases. Flux pulsation loss decreases because pulsation flux is decreasing. Because pulsation flux decreases. Point number 4 is unbalanced magnetic pole. Unbalanced magnetic pole, UMP. So if length of air gap is small, if length of air gap Lg is small, then even though small deflection small deflection or eccentricity of the shaft. The shaft produces large irregularity in the length of ear gap. ELG produces large unbalanced magnetic pole, which may bend the shaft. So if ELG increases, length of ear gap ELG increases, then small eccentricity not producing much magnetic unbalanced pole. If ELG increases, then small eccentricity not producing eccentricity not producing much magnetic unbalanced pole. Point number 5 is cooling. If length of ear gap, if ELG is comparatively large, better is the cooling. Point number 6 is noise. So noise causes variation of the ear gap. Now relations for calculation of length of ear gap. For a small machine, the length of ear gap ELG can be calculated using following empirical formula. Number 1, ELG length of ear gap is equal to 0.2 plus 2 square root of D into L, Lg in mm, whereas D, diameter of stator bore, diameter in meter, and L is length of core, stator core. This is also in meter. So D and L will be in meters, but Lg will be in mm. Second formula, this is also empirical formula. Second formula is Lg is equal to 0.125 plus 0.35 D plus L plus 0.015 VA, Lg in mm, where D and L are same, stator bore diameter and stator core length in meter, and VA is the rotor peripheral speed. VA, this is rotor peripheral speed. This is second formula. Formula number 3, length of ear gap Lg, this is equal to 0.2 plus D. This is also mm, D in meter, D in meter, and the formula 4, this is for the machine with journal bearing. This is for machine with journal bearing. Here Lg, length of ear gap Lg is 1.6 into square root of D minus 0.25 Lg in mm. Again D in meter, D in meter. Now rotor diameter dr, this is rotor outside diameter dr, can be calculated. Rotor diameter, this is dr, can be calculated as, this is dr, this is equal to D minus 2 times Lg. This is for rotor diameter dr, or we can say this is the stator inside diameter, this is stator outside diameter, this is stator inside diameter, this is outside this is stator inside diameter D. This is one of the main dimension D. Rotor is here, this is rotor outside diameter, and this is nothing but dr, this is nothing but dr that we have to calculate. This is dr. So dr is stator inside diameter minus this, and this is nothing but length of ear gap between rotor and the stator. So this is nothing but Lg. This is also Lg. This is rotor surface, this is stator inside surface, this is nothing but T, and this is nothing but Lg. This is also Lg. So this is rotor. So rotor diameter is D minus twice Lg. Thank you. The remaining part of the rotor design, that is rotor teeth, rotor core, rotor slot, will be studied.